All right, good. There we go. And I'll mute them. All right. So I got a few minutes for the official starting time here. And there's, as always, lots of news. This is the big one, of course. There's a big Docker flaw. You can take over administrative rights on the host from inside a Docker container. And people are very worried about it. Apparently, from the little rumors I'm seeing, this has been known for weeks, but kept secret until a couple days ago. So there's one proof of concept out, and apparently a bunch of stuff is ready to show, but they're all just not telling any of us until they get all the patches out. So we tried to set this up last night. We couldn't quite get it working. But it does look relatively simple, and everybody is rushing to patch it because it affects all the cloud services. Boston, this private college cut completely for running out of money, and City College is not far from it. They're having huge cuts, firing about half the teachers, or some large portion of them in various departments. We're going to know more next week, but the classes we offer are going to greatly change. And nobody really knows what's going on yet, but there will be big cuts and big changes next semester all over the college, and more cuts the semester after. I tried to bust out of a Debian container. Yeah, it's Caitlin. Yeah, and I even found a video of the proof of concept, but it still wasn't very clear. Nobody seems to quite be telling us everything we need yet, which from past bugs like this that I've seen, I suspect what's going on is they weren't supposed to tell us anything yet. And most of them are honoring that, and just a few people are leaking parts of it out. Because really, since the patches just came out, it would make sense to not release the exploits for maybe another week so people have time to patch. Anyway, we'll talk more about Ethereum later, but Ethereum is going through a big change. Ethereum has been trying to change their consensus algorithm from proof of work to proof of stake, which would do something about the vast amount of electricity wasted and all that. But it turns out there is no current model for proof of stake that works. Somehow proof of stake would be betting some of your money on your mining so that people would be kept honest by that instead of just by competing to see who could do it the fastest. And several of the proposals have been proven to be defective. And the Constantinople upgrade is going to come. And they're pushing some version of it out soon. But there's some chaos on the Ethereum blockchain. Also, Ethereum seems to be pretty much abandoned. Most new distributed apps do not run on the Ethereum blockchain, so they do need to do something to improve their scaling, and they seem to be sort of floundering around trying different things. The SGX is an Intel feature that sounds very much like the secure element in iPhones. It is a special coprocessor you can put cryptographic processing in, and it's not a coprocessor, but part of the chip. And the threat model was you would have trusted stuff in the SGX and apps outside it would try to attack it. And these guys reversed the threat model where they put malware in the SGX. And that turns out to be very effective, of course. So we'll see how this proceeds. But we'll be talking more about that tonight and throughout this course. This is a very common attack against cryptography, is to violate the assumptions made by the person that designed it. And that usually does it. Bruce Schneier has come out against blockchains, which is not a big surprise, but he's a very influential fellow. And NIST has come out in favor of blockchains, which certainly surprised me. But this is the project that one of my students at another college was involved in, a teacher. This is the blockchain for military supply chains. And that does seem like a fairly sensible plan. You have a small group of people that are trying to agree on providing parts for something, and you want to just have a good ledger they all agree on. What Bruce Schneier says is there's no reason to use a blockchain for this. You could just as well use any other kind of database for the cryptographic signature on it, and that could very well be. But anyway, NIST has now approved it. Anyway, now we're up to the official time, so let's move on to the cryptographic security. This is why I love this book. This is a very good book. He kind of addresses issues that are not in other books. Other books just get into technical mathematical details, but they don't talk about what it means, and he talks about it more. So what is security? In the world of cryptography, this turns out to be quite difficult to define. And the bottom line is that everything is a whole lot less certain than you would think. I thought of mathematics as being perfect and certain, but it's not that perfect at all. And because you're trying to define slippery concepts, like you would like to say it is impossible for the bad guy to steal the data, but what is impossible? So here's different types of security. Informational security is what you'd really like, where you somehow prove in a perfect theoretical sense that no possible attack from the bad guy will steal the data. That would be nice. In practice, you almost never can get that, so you settle for some kind of approximation of that, practical impossibility, where you have some degree of confidence that it would cost too much for the bad guy to get in or take too long. That's what we really have, and we're going to talk about the procedures that are actually used for that. So that's informational security. This would be a sort of perfect form of security where even an attacker with unlimited time and unlimited resources would still never get in. And the only one I know that has this property is the one-time pad. Because if you try every possible key on the one-time pad, you will create every possible message. And so one of them is the right message and all the rest are perfectly good-looking wrong messages, and you have no way to tell the right message. So it is in principle impossible to crack it without knowing the key. So that's good, but we cannot really use the one-time pad because the key distribution problem is such a drag that it makes it very impractical to use. So we settle for this with things like AES 128. And this is just a statement that right now there is no way to do it on any known hardware in any reasonable amount of time. And therefore we can have reasonable confidence that it's secure, but of course, you do know there are secret agencies like the NSA and other nations' secret groups that have special hardware beyond what the public world has, and you really don't know what they can do. So you're just guessing here. And AES right now is considered computationally secure because there is no way to do 2 to the 128 calculations on anything. But quantum computers can test those keys with only 2 to the 64 operations if they ever get working that well. The current quantum computers cannot do that at all, but they're early prototypes and they're getting better. So perhaps within a decade or two, there will be a quantum computer that can really do the 2 to 64 quantum calculations required to crack AES. I mean, and that is true. AES will stop being computationally secure, and we'll have to move up to the longer version, AES 256, or perhaps to something else entirely. So you can now quantify security. You can define security with the number of calculations an attacker performs and then the probability of success. So if AES 128 has no weakness, then the only way in will be to try every possible key, and that will mean you have to try 2 to the 128 keys to have a 100% chance of getting in. And so you'd call that, that's one way to express it mathematically. And of course, that's why you'd be kind of foolish. You could define something, you say if you try 1% of the keys, you have 1% chance of getting in. But normally the thing you talk about is you want to have a 100% chance of getting in. That's the number you quote. So you usually just set T to 1. You set the probability to 1. So if you try one key, you have a tiny chance of getting in, 1 in 2 to the 128. If you try 2 to the 64 keys, you have 1 in 2 to the 64 chance of getting in, which is still almost nothing. Trying T to 128 means you're absolutely going to get in, and that's the normal number you quote when you say it has 128 bits of security. That means if someone could do 2 to the 128 calculations, they would get in every time. So that's the simple way to quantify it, and that's the point. Just set that success probability to 1 and quote the number of operations it would take to get in. This is an approximation, a very approximate measure though, because that is just the number of keys you have to test, but different ciphers have a different amount of computational time and memory and such required to test a key. So 2 ciphers with the same number of bits of security aren't exactly equally secure, but you don't really care about the exact value of this number. You just want the order of magnitude. You want to figure out what the maximum you think your attacker could ever do and make sure that you're significantly above that. You don't really need to precisely hit it. So here's some examples of serious failure. WEP is a famous one. WEP had a so-called 128-bit version, which really had a 104-bit key. And if that was true, if it really gave you 104 bits of security, it would be completely fine. Anything over about 100 is essentially uncrackable at the moment. But there was a series of mathematical flaws in WEP that meant you didn't really have to try every key. So in 2001, they got that down to 2 to the 20. In 2007, they got that down to the 2 to the 15, which is a long, long cry from 2 to the 104. So WEP is worthless. It's trivial to crack even on any kind of computer we've had for the last 20 years once you find these more powerful attacks. The key is long enough, but key length is not everything. You also have to have an algorithm that does not allow you to have any kind of shortcut where you don't have to try every key. The substitution cipher we talked about before. If you just replace every letter in the alphabet with another letter in the alphabet, you have 26 choices for the first one and 25 for the next one and 24 for the next one. That turns out to be 2 to the 88 possible combinations. If the key space is all that mattered, this would be really quite strong, but you can crack it with no computer at all because you can just look at the text and find a 1 or 2 letter word and guess what letter that is and then fill in the letter and gets the next one. So there is an algorithm that gets you to the end without trying every possible combination of letter substitutions. And again, that's the point. Key space is a sufficient, but not a necessary, but not sufficient condition for security. If your key space is too small, then it's never going to work. Like the DES, where the key space is only 2 to the 56. But if the key space is large enough, you might still have a weak cipher because there's a shortcut. So RSA 2048 has another issue here. Public keys do not match the length of the key with the length of security at all. RSA 2048 has about 100 bits of security. It is not directly related to the 2048 because you cannot use all possible keys. The keys are not just 2048 random bits. The key is actually the product of 2 prime numbers, and that does not make every possible key available. So the mathematical strength of the key is more complicated than just taking the number of bits. And so I actually contacted the author today on Twitter. He's on Twitter, and he paid attention because the official government recommendation says that RSA 2048 is 112 bits. And he said it's less than 100 bits. And I asked him, and he said, well, it's just an approximate number. Those are both essentially the same, which is a good answer. And I really appreciate him answering me so promptly. And I put this up here because I wanted to remind you folks of something. When I was a younger security researcher, maybe 10 years ago, I would respond to people like this by just being rude and saying, hey, you're wrong, you're an idiot, you got this wrong. And I finally wised up. That is not the way to get things done. You have to be very humble and very polite when you go to people. You have much better results. And the last couple of times I found what I thought were mistakes in textbooks, I've ended up on good terms with the author when I approached them very humbly saying, gee, I don't understand this statement. Isn't it supposed to be like this? If you're very respectful, one guy offered me a job, said he'd hire me to help fix problems. It seems important to be harsh and condemnatory when you're new to the field. After you've been around for a while, you begin to realize that being gentler is much better. So I thought I'd mention it. I've seen, there was a case about 8 years ago, maybe 6 years ago, where I was on Twitter and a friend of mine said, everybody should be using HTTPS. Why isn't Amazon using HTTPS? And I said, yeah, I think Amazon should use HTTPS. And Dan Kaminsky came in and said, oh, no, it's too much bother. You can't really expect them to use HTTPS. And I was very surprised by that. And this other guy said, well, Dan Kaminsky is just stupid. And I said, no, that's not the explanation. I'm surprised he said that, but he's not stupid. And, I just wanted to mention it. Don't be harsh and insulting with people. You'll have far better results if you're very gentle, because then you can make a friend. And often, if you think somebody's wrong, it turns out it's just you that was wrong anyway. So here's the official U.S. government recommendation. National Institute of Standards. The original government document is, of course, sort of ponderous and hard to read. This is a summary somebody made. So 1024, RSA 1024 is considered to give you about 80 bits of security, which is no longer good enough. So most people have moved up to RSA 2048, which is the current recommendation. And if you want 128, you go to 3072 or some higher number. And the general rule is something above about 112, 128. That's good enough right now. 256 is a very comfortable margin above that, which people do if they're very concerned about things because they regard the data as very high value, like national security secrets, and they expect somebody really powerful to attack it, or they are hoping to protect this data for a long time. And you see up here, they consider 2030 to be a stage, which I think is because that is somebody's estimate of when there's a chance of them being significant computational improvements, like maybe quantum computers or something. So if you only are protecting your data through 2030, you can use what we're using now. If you're planning to protect this data beyond 2030, then you should use something significantly stronger to give yourself some wiggle room as computers get more powerful. And that's the point. The full attack cost is not included in those bits, and here's the other things that make the real attack different. One simple thing is parallelism. If certain computations require you to do step 1 before you do step 2, and you have to do step 2 before you do step 3, and in that case, you cannot get any good out of having more than one processor. But if you have independent steps, where like DES, there was a DES crack that took place in 1997. They got 10,000 servers to attack a 56-bit key, and they split the job up into 10,000 small jobs, and each independent server hit some of the key space, because you could totally do them independently. So that's a parallelizable calculation. And even on very slow computers, by having many computers do it at once, they were able to get to the answer in less time. The total amount of processor hours was the same, but if you can parallelize it, you can save time by using more processors. And these days we have multi-core machines, and even 10 years ago, I heard about 64,000 core machines for research projects and stuff. So, and there's GPUs that run heavily in parallel all over the place. So you can do a lot. If you can parallelize your calculation, that greatly changes the amount of time required. And then there's the issue of memory. You can slow things down by making them use a lot of memory. You can burden people by just making the calculation very memory intensive, so they just have to pay for a lot of RAM. Or you can make calculations faster by putting stuff in memory to look them up. The memory affects it quite a bit. And Ethereum mining is memory intensive. This is intentional because Bitcoin is done only with CPU, because it's just SHA-256 of SHA-256. And that means Bitcoin, people made these ASICs and have these special mining rigs. And the only thing that limits the efficiency, the speed of Bitcoin is the price of electric power. And they didn't want that to happen with Ethereum, so they made the hashing algorithm memory intensive, which means that it's not so simple for one country or anyone to dominate it. And anyway, that's the game here. Then there's pre-computation, like rainbow tables, time memory trade-off, where if there's a certain if you're going to try every possible key, and it turns out that some of the calculations are the same every time, you can save yourself a lot of time by just making a table of those calculations, just looking up the answer instead of repeating them every time. And there's quite a few versions of that. And for example, this is true of Windows password hashes. Microsoft Windows did not put any salt in their hashing algorithm, and they've never changed this. This is the original Windows NT 3.5 algorithm, which is still used. So if I go down here and I add a user with a password of Apple 9, and I could take the hash out of the system, it NT hashes that long value there, starting with 44, and that value, you can get it from Kane, a hacking tool, or at PWDump, or a bunch of hacking tools. And when you get it, all you have to do is go to an online cracker, and you can get the password. On the far right here, it's kind of gray. The Apple 2 shows up, the Apple 9 password. They have something like 100 billion passwords in their database. You can just look it up, because everybody with a password of Apple II has the same hash, and people have accumulated over the last 25 years big tables of pre-computed Microsoft Windows password hashes. So if your password has ever been used before and added to one of those tables, you can just look it up. You don't need to calculate and hunt for it. And that's the problem. That's why you should have a cryptographic nonce, a random number, included in every calculation, so that if someone else calculates starting from the same password, they'll get a different hash, and you can't make a master list like that. But Microsoft did not do that for some reason, and they have ignored the many people yelling about it, including me. None of us can make them budge. All right, so here's another problem. You might want to get on in just one account, but you might be willing to get any of many accounts. For example, you're trying to break into a company, you dump their entire Active Directory domain, you now have 1,000 accounts, and you'd be happy to get any one of them. Well, then, of course, you can get in 1,000 times faster, run whatever your attack is, and see how long it takes you to find one of those hashes. So that's another issue. All right. And so anyway, here's the current levels of security. Cryptographic algorithms are typically designed for commercial use, for government use. So they design them to specifications, specified by the National Institute of Standards, really. And even the ones that don't end up approved were designed in the competition. So they typically come only in two sizes, 128 and 256 bits, because that is the normal security and the extra high security, and that's all we care about. Anything weaker is no good for anything. Anything stronger is just a waste of your time by modern standards. So that's typically the sizes you get. So let's try some Cahoots. Let me see if I can get my, here we go. I should have Cahoots open someplace. I do. All right. So we're here, and I should be able to play my glorious Kahoot music. There we go. Good. And almost everybody's online, but I have a couple people in the room. So on we go. I'm glad the Kahoots work for online viewers. Get a list. Oh, that's not it. Okay. All right, I might get up to 12 or 13, but that's going to be about it. Are you connecting to the Kahoots? All right, I'll wait a little bit. We got plenty of time. Give it a shot. Make it online?
It's working. Okay, so the website is
Kahoot.it. Looks like something's wrong. Okay. That you? No, not yet. Okay, good. All right, I think we got everybody that's coming. Let's go ahead. So, all right, how secure is AES? Okay, it's computationally secure, which means that as far as we know, it is not possible with any reasonable amount of time to get in. But it's not 100% proven at all that you can't get in. All right. What kind of security does not change as technology improves? Okay, that's the informational security. That's where it's absolutely impossible to get in with any amount of computer time, so faster computers don't change the situation. How many bits of security do you get with, oh, that should be RSA 1024, pardon me. That's not 128, that should say 1024. RSA 128 is ridiculous, nobody uses that. Okay, you get 128 bits out of RSA 1024. RSA was originally written for 512. You could, in fact, do it with 128, but that would be ridiculous. Nobody would use it. All right. How long should an RSA key be strong enough for normal use now? Okay, right now, it's considered 2048 bits is what's recommended. All right. So, one more. What cost is intentionally large to make Ethereum more secure? Okay, they deliberately made it a memory-intensive algorithm in an attempt to prevent one of the flaws in Bitcoin from happening. All right, so I've got food. I think I know who that is. Yeah, good. And WITV, I know who that is. And I know who Caitlin is. Okay, good. All right. Just going to put this down here. All right, so let's go back. Yeah, we got time to continue with the slides. That's good because I want to finish this and then I want to demonstrate the RSA today, which we'll talk a little bit about here and do more later. So, all right, so since you do not have generally the mathematically perfect proof of security, you instead settle for just sort of some reasonable argument that justifies your security, and you can either do it with a mathematical proof or with something called heuristic security, which is just meaning people have actually tried to crack it and they failed. So a provable security means that you have a mathematical proof that this problem is related to some other problem, and therefore it's at least as good as the previous one. So this is what you might do to develop future cryptographic schemes from first things. So once you have some mathematical activity that you have some confidence in, you can derive more things from it and prove that they're as secure as the previous one. So RSA is based on factoring number units component primes. And it has never been proven that that is impossible to do in a fast way, but no one has ever found a fast way, and they've been trying since the time of Pythagoras, 2,000 years ago. And all that time, no mathematician has ever found a way to solve this problem quickly. So we have reasonably high confidence that they can't. There is, in fact, $1 million prize for someone who solves this mathematical problem of how to prove that something is really hard. Right now, there is no way to really know that something is hard. All you know is that nobody has figured out a smart way to do it yet. But maybe somebody will find a smart way to make it faster, and then everything based on the assumption that it's hard will fall. So the RSA algorithm, which we're going to start using in the projects here, works like this. You choose two random large prime numbers, P and Q. Then you multiply them together, and you have N. N is now a really long, if P and Q are 100 digits long, N is now 200 digits long. And it turns out in practice that nobody can figure out P and Q from N. That's the factoring problem. So now you choose an exponent, which could be almost anything. And in practice, almost everybody just uses this number, 65,537. It turns out to be unimportant. It doesn't have to be random or vary or anything. And your public key is N and E. You tell everybody N and E. They can encrypt stuff. You can only open it with the decryption key, and the decryption key requires knowing P and Q individually, not the product. So to encrypt something, you take your plain text X and turn it into a number, then you raise it to the power E modulus N. And this is why in the math parts in the previous lectures, we started doing some modular arithmetic, so you get used to it. E is the encryption key, which is that, and you take it to modulus N, which is that number that's P and Q. To decrypt it, you take it to an exponentiation again, to a power D mod N. That takes the ciphertext Y and turns it back into plain text. So the security comes from the fact that even though everybody knows E and N, nobody can figure out D. Now D is of course mathematically related to E and N, but it's mathematically related in a way that as far as we know cannot be done backwards. You have to reverse N to P and Q to figure out D, and that's the step that nobody's ever found a way to do fast. So that's why it works. And so You can compare one crypto scheme to another, and like that, you might prove that RSA is strong because you could only crack RSA if you could solve the factoring problem, so it is at least as strong as the factoring problem. That's the mathematical proof. So that's a game, and that's one game to give you some confidence, and we use this a lot. You can generate symmetric algorithms, random number generators, and hash functions, all from the same fundamental mathematical activity, and you can prove that you can trust all those other things as much as you trust the original activity. There are, of course, problems. You started from some kind of mathematical system, and that might be broken. It might turn out that it wasn't as strong as you thought, and that everything you derived from it is also not as strong as you thought. You might overlook an attack. This happens a lot, that when you actually build hardware that does it, it turns out that something else happens that makes it possible to find the key that was not in your mathematical model. This is really big. Your mathematical model is this perfect abstract system where the attacker only has access to certain information, but in the real world, attackers have opportunities to do other things. And of course, you might just make a mathematical mistake in the proof. This happens pretty often. So here's examples. If you have P and Q created, and we already talked about this in previous classes, I think this turned out to be true of the whole internet until a few years ago, that tons of public keys on the internet were the same, related, because when people tried to make the random P's and Q's, the random number generators were not good enough, and with a high probability, like 1 in 1,000, they would get a duplicate random number, which ruins the whole thing. If the numbers aren't really random, then you can find them. Knapsack was something invented by Merkle, and you might remember Merkle is the guy that invented the Merkle tree, which is the foundation of Bitcoin and all cryptocurrencies, which I don't think he designed it for that purpose, but he did design the Merkle tree, and he made a cryptographic system called Knapsack, which was later completely broken by a later mathematical technique to more quickly factor it. So this is what everyone is really worried about with RSA, is you're trusting that nobody can factor a prime number, but somebody can figure that out, factor a number to its component primes, and if they did, it would all be over. Then, of course, side channel attacks are all over the place. If someone can measure the power consumption, the radio waves emitted, the time it takes to compute, all these things can leak out information about the key, and the math doesn't consider that. The math just considers these perfect numbers unless you somehow incorporate those other things in your math. So real gadgets using a cryptographic system are not really exactly equal to the model that was used to design that system. And therefore, there are weaknesses that are not mathematical errors. They're approximations made when you actually build a gadget. So I find this to be extremely common. If you just implement cryptography incorrectly, I've been finding most Android apps do this, and here's many of the Android apps we're doing in the Android class. All these apps encrypt passwords and store them insecurely because they implement the encryption wrong. This is very, very common. And that's why I decided to teach this class, because it's obvious that so many practitioners, developers, and managers do not understand the basics of cryptography, and they'll let people design something that uses cryptography foolishly so it doesn't protect their stuff and just call it done and move forward. Whereas if anybody at any level in the authority chain actually knew anything about cryptography, this nonsense would not happen. It's very possible to encrypt things so nobody can get in if you just have to apply the algorithms correctly. All right, so then there's heuristic security, which is where you say skilled people have tried to break in and they couldn't get in, so now we trust it. That's where AES is. Most symmetric ciphers don't have a security proof. They just have this. So instead of being able to say mathematically having proven that it has certain levels of security, we have this thing called a security margin. You take the algorithm and people attack it and they can't get in. So now you weaken the algorithm somehow. Typically, algorithms have a certain number of rounds of calculations. So you do less rounds until you can get in. And then you figure out what is the most rounds I can crack, and so how many more rounds are we above that? And that's called your security margin. That is a very rough approximate measure, but this is some way you can guess which algorithm is more secure than another. So AES, for example, Bruce Schneier wrote this a few years back. He's very easy to read, one of the authorities. So AES 128, as far as anybody knows, has got nothing wrong with it in the sense that there is no way to get in without trying 2 to the 128 calculations. And that is rather rare. That means the actual mathematical algorithm scrambling the bits is really quite effective, and there is no shortcut. AES 192 and 256 do not have that privilege. They actually can be cracked with a much smaller amount. It should take 2 to the 192 calculations to get in AES 192, but in fact it only takes 2 to the 176. And AES 256, it even takes less, 2 to the 119, because there are shortcuts. And that's not good. but they're all effectively uncrackable at the moment. But that test is on 11 rounds of AES 256. So there's a safety margin of 3 rounds, if you want to look at it that way. That's the margin of security. AES 256, the kind that can be cracked, if you want to say getting it down to 219 counts as a crack, which is not really fair, because nobody can do 219 calculations. It's just disturbing because it should be much stronger. But that was even 11 rounds. So you can see the margin of security there. There's a couple of ways to measure it. But that's what we do. And if you think about this from a mathematical pure point of view, this should be pretty disturbing. You'd like to have mathematical proof, and what we have is this sort of hand-waving rule of thumb, and then this idea that adding more rounds makes it harder, and we count the number of rounds, and we don't even really know how much another round means. And by the way, there are plenty of things where more rounds make it weaker, like XOR and Route 13 doing it again undoes it. So it's not necessarily true that adding more rounds makes it safer. So, there's a lot of disturbing things going on here. Then there's the generating keys. I already mentioned. How are you going to generate keys since you don't really have any randomness? One thing is use random number generator. Another thing is take a password and run it through a function and generate a key from that. Another thing is these key agreement protocols, which we'll see is Diffie-Hellman, and RSA uses it, where 2 people over a network trade messages to agree on a key without either one of them generating the key all alone. These are various ways to do it. If you think about the random one, you can just do it in OpenSSL. It's very easy to do. You can just make random numbers as long as you want. They're very fast. The pseudo-random number generator just zips them out. You can have as many as you want. And that's fine. For symmetric keys, it's all very simple. Make a random key, and the number of bits of security you get is usually equal to the size of the key. For asymmetric keys, it is not that simple at all. RSA in particular, it is actually very difficult to find the key. And let me just show you how slow this is. This is pretty horrible. Let me bring up my Mac, and I bring up Python here. I can import. I think I'll just type it in. This is how you do public key encryption in Python. That's why we're going to use it a lot, because it's extremely simple. From crypto.public key, import RSA. All right, now I can set a key equal to RSA generate, say 2048, which is what's recommended these days, 48. Okay, now that took less than a second, but what it had to do, it did not take 2048 random bits. What it actually did was make a 1024-bit number and then test it to see if it was prime, and the chance that it was prime is less than 1%. So it had to make hundreds of 1024-bit numbers until it found one that was prime. And then it had to do that another time and then multiply them together. So it did hundreds of calculations to generate that one key. It is really laborious to do because there is no algorithm to generate prime numbers that's secure. It's a probabilistic thing. You have to generate a number and then run it through a whole series of tests. And it might take 3 or 4 or 10 cycles of testing to decide if that number is prime. Although with a good test, you can usually do it in 2 or 3. But this means it's very slow. So let me blow this up to make it easier to see. And let's just see how slow this is. That one took less than a second. Let's take 4096. That took about 2 seconds. If I do 8192, 2, 3, 4, 5, like 5 seconds, it's taking a long time. It gets up to a really long time if the key gets longer. So it's really doing a lot of work to generate those public keys. And we'll go into that in more detail later, but it is a thing to know. Public keys are much more complicated and in a lot of ways a lot less secure. But at the moment, 2048-bit RSA is considered unbreakable. So then you have to protect the key. So after you've generated this key, you have to store it somewhere, like on a server or something, or on your thumb drive or somewhere. So how do you protect it? One thing people do is protect it with wrapping. So there's another password needed to open the key. So there's another layer of encryption on it, and that key is generated from password. Another thing you can do is not store the key anywhere, just base it entirely on a password you remember. So the only memory is you. This is how Bitcoin memory wallets work. The original Bitcoin system made random numbers for every account you made. And you had this whole bunch of random numbers you had to save, and people would lose the numbers and lose their coins. So they switched to memory wallets, where you take a password and you hash it to make a key, and you hash it again to make the next key, and again to make the next key. So as long as you remember the password, you can always get all your keys back. which means you're less likely to lose your keys, but it also means now someone can find your keys by guessing your password if your password is not long and complicated. So you, as always, you trade one thing for another. Another thing you can do is just store your keys on some object, like a smart card, a USB dongle, and then hopefully that has a password. That's another way to do it. All right, and so here's things that can go wrong. You might have an error in your proof. There was a system called OAEP. I forget what it stands for. It's in the book. This was proven to be secure, and years later, someone wrote a paper and proved that the math was wrong, and it was in fact not secure. And the proofs in the original proof to make it secure were invalid, but the way it was actually implemented turned out to be secure by accident. So the math was wrong, but it didn't really matter. This, by the way, is another reason why arrogant security engineers are so unwise, because you'll go and yell at somebody like Amazon for not using HTTPS, but the fact is very many people have thought of this and they put in another control further down the line so that even if people get in the first step, there's another layer of defense behind it. So even though in principle something is being done in a weak way, it does not really mean that it hurts them. You cannot really buy products or cheat them because they thought of that, and that's the case here. You mean something was wrong, but it didn't really matter. That happens a lot. And in well-designed systems, that happens all the time because you don't trust any of your defenses and you have layers of defenses. So even if one fails, another layer will catch it. Another big problem is this. If you have deliberately weak cryptography, which unfortunately everybody does because of the Clinton administration. The Clinton administration tried to pass laws to make it possible to do business on the internet. And one big concern at that time was that we would export weapons-grade cryptography and allow our enemies to hide from us. So they had a belief that they could hide strong cryptography from our enemy nations, which is a very strange statement to think that we're going to hide math from the Russians and the Chinese, but apparently they thought we could do that because I think the government leaders just did not understand what they were doing. But they did create this thing called export-grade cryptography, so every operating system, like Windows and everything else, had a mode that would generate these weak keys. So now the internet had a bunch of servers that were using weak breakable cryptography. And therefore, if you wanted to see those websites on those servers, you would have to allow weak cryptography in your devices. And now, decades later, many servers still have those weak cryptographic standards on them all over the place. And it turns out there are a bunch of downgrade attacks where I can just connect to a server and tell, oh, I'm sorry, I'm Windows 98. You have to tweak a really old cryptographic system that's not secure. Or I'm an export version of Windows, and I can't use strong encryption. So you can trick servers into using weak old encryption. This is one of the many reasons the cryptographic community tends to be very, very, very angry at the government. The government has done many things that foul up cryptography. This is one of them. So I got another set of cahoots, and then I'll demonstrate some RSA stuff. All right, which is here. Yeah, the wall's in the news, isn't it? Guess I'll wait a few more seconds. I think maybe I got everybody. Yep. No screams of protest. All right. All right. So what property means that experts have tried and they can't get in? Okay, that's heuristic security. It's not very reassuring because it might just be that somebody else has smarter experts than you do, but for what it's worth, that's one kind of security. All right, what number do you have to keep secret in RSA? P is the secret. P and Q are the prime numbers, N is the product, and E is the other public key. N and E are public. P and Q have to be kept secret. And we'll play with this in a few minutes and do some RSA. All right, what operation turns a password into a key? Okay, that's called a key derivation function. It's PBKDF2 is the main one, password-based key derivation function, and we're going to see it a lot when we get into Android cryptography. That's how people do it. And it really is the same thing as password hashing. But anyway, that's a key derivation function to turn a password into a key. And which operation protects a key with a password? All right, that's key wrapping. All right, so that if somebody else gets to use your terminal, they can't just steal your key easily. So I've got the wall. They're going to have to tell me who they are if they want their points. And I got M dot, I know who that is, and Foodie, I know who that is. I bet it's the same person as Food. All right, so I got the Kahoot winners, except for the wall, who will have to come out of the closet if they want their points. And let's do this, take a look at this RSA project, which is here. So there's some Windows-based stuff where you do the simple things in AES, and I want to talk about this RSA one that's due next week. So here's the RSA algorithm. There's going to be a whole chapter in it later where we'll go into it in a lot more detail, but you might as well start using RSA. Here's how it works. You have a public key, which is N and E. These two numbers are what you tell the whole world. Anybody in the world can now send you secrets. So when you do that RSA key generation, which I did in Python, it generates a public and private key. The public key is this. The private key is P and Q, and it's D is what we really care about. D you have to create from P and Q. So you calculate N from P and Q. Then to get D, you calculate this thing called phi of N, because it turns out that you cannot reach every possible number on a circle of size N. With P, N is composed of two prime numbers. There are certain numbers that will, for example, if you have a clock with 12 dials on it and you jump by 4s, you will never hit 1. You'll go from 0 to 4 to 8 to 0. So if you had a circle of N and N is not prime, some of the numbers you might wish to jump by are forbidden. You can't really reach every possible number. So anyway, this phi of N is actually the number of values you can use on that circle of N that will have the property of mapping every number to every other number sooner or later. It turns out the others are not useful for cryptography because you really can't get anywhere. You could encrypt something that you couldn't get back. We'll talk more about that later. But that's why you create this number phi, which is a little bit smaller than N. And then you have to find this number, D, that undoes cryptographic operation. D times E is 1 mod phi. This is what reverses. So if you take something to the power E and you want to reverse it, you take it to the power D after that, and that will undo it. That's the point of this in general terms. We'll get more details are coming later. So let's just do it here. We're going to choose really low numbers of 7 and 23 for the prime numbers. So we're not going to make a strong system. We're just going to go through the steps so you see how it works. This is RSA with very small keys. So if I set P equals 7 and Q equals 23, Q equals 23. I'm going to copy and paste from now on so I don't have to type clumsily. All right, let me shrink my window. There we go. All right, so now I'm going to calculate N and print it all out. And actually what I want to do is use Kali. Oh, I'm in Kali. Good, okay. I wanted to use Kali instead of the Mac because Kali lets me copy multiple lines and it doesn't foul them up. So I have to define my P and Q. Let's get the whole story. Now I can do 4 lines at once in Kali. If you do it in the Mac, it works, but it looks ugly. All right. So P equals 7, Q is 23, N is P times Q, and here we are. P, Q, and N. And by the way, just by convention, P is the smaller prime number. Q is the bigger one. There's no real reason for that, but that's the convention. So this is P, that's Q, and this is N. So now I have N is 161. Now, I'm going to calculate phi. Phi is P minus 1 times Q minus 1. So it's going to be a little bit smaller than N. So N is 161, but phi is 132. Now, I need to select a public exponent. Like I say, you can just pick a number. I think it helps for it to be a prime number. 5 is fine, 3 is fine, 65, 537 is fine. We're just going to use E equals 5. Now, if E is 5, what we have to do is find a number D so that D times E is 1 modulus phi. That is the magic key that will undo the cryptography. So to do, now there are actually algorithms to find it, but we're going to find it by just a brute force search. So let's consider this. I have my phi is 132. So that means I have, let me shove this out of the way for the moment. I have a ring like this that goes from 0 to 131 and then back to 0. And here's 1. And I want to find a number, and my E is 5. So I start at 0, I start multiplying by 5, I get 5, 10, 15, 20, 25, 30, up to 120, and then it wraps around, and I end up at something like 4, and wrap around again. Eventually, I'm going to get to 1. So what do you have to multiply 5 by to get to 1? So we can do this. Let's try various numbers just to understand what the modulus is. I'm just going to calculate various things modulus phi. So let's do this. All right, so 100 modulus phi is around here. That's just 100. 130 modulus phi is right here. Here's 131 modulus phi. 132 modulus phi is 0 because we've wrapped around ones, okay? So 133 modulus phi would be 1. That's how modulus works. So now I'm trying to find something which when multiplied by E will produce 1. So if I take 20 times E, that's 100. So 20 times E, modulus phi is just 100. So it's bigger than that. So I can just try 21, 22 and go till I pass 0 and see if I hit 1. This is one way to get there. So I made it up to 115, 120, 125, 130, and then it wrapped around and gave me 3. I did not hit 1. So I was not able to find an inverse in the area of 20. Now I'm going to have to go all the way around. So I have to jump forward by about another 20. And so I'll have to go down to something like, it turns out around 25 is where I hit here. So around 50 is where I'm going to hit it, the region of 1 again. So someplace up here around 50, if I'm lucky, I'll find something that produces 1. So you see here's 50 gives me 118, 51 gives me 123, and 53 gives me 1. So I found my inverse. The inverse, the D key is 53. And so I can now do cryptography. Here's the game. So Megan's public key is 161.5. That is N and E. And she announces this number, and anybody can now encrypt a message and send it to her. She knows these secret numbers. P and Q and phi and D are all secrets. She knows them. Nobody else knows them. So anybody can now send a secret to her. So Cubo wants to send her a message of hi. Now, you have to somehow turn that into numbers, and there are various techniques. In this case, I'm just going to turn each ASCII letter into one ASCII number, which is a pretty simple procedure, but it'll do. So H is 72, and a lowercase I is 105, and the exclamation point is 33. So there's my message turned into numbers. And now I can encrypt those numbers. Here's how you encrypt a number. You take the message in plain text, which is X, you take it to the E mod N. And this is the public key, N and E. So this is the encryption routine for those 3 letters. It takes 72, 105, 33, and it turns it into 151, 119, 157. That is the encrypted message, which anybody can create, but nobody can open without the private key. That's the idea. So now these 3 numbers can now be sent to Megan through an untrusted medium like the internet, where attackers will see it, and it doesn't matter because they don't have the private key. That's the idea. To decrypt it, Megan takes the ciphertext to the D mod N. And that will undo the previous calculation, which took things to the E mod n, because E and D together are 1. So what she does is take these three numbers, 151, 119, and 157, and takes them to the D mod n. And she gets back the original numbers, which is 72, 105, 33. So that is the system. Now, of course, this is not secure because these numbers are small and you could easily try all possible values and factor it, but this shows the point. It is extremely wonderful. One of the great things about RSA, I've loved ever since it was first created, and I first heard of it, I think when it was new in 79, is the math is very simple. You don't need to learn anything weird. It's just exponentiation. And it really works. It's completely unbreakable as far as anybody knows, even now, as far as the mathematical part of it goes. So anyway, now you can decrypt a message, and there's a series of challenges you can go through here to do more and more and send these messages, these simple little RSAs, and I highly recommend doing it. I remember I taught this stuff at DEF CON last summer, and I kind of skipped over the RSA because I thought it was pretty old hat, and we talked about quantum cryptography and stuff, and I noticed afterwards I went to like a pizza place, and the guys that were doing this RSA stuff are very interesting because this really matters. Now, the old-fashioned stuff, this is what people really use. If you want to get to the bottom of cryptography, you just need to learn how to use AES and RSA correctly, and that's probably all you really need. You just use that for whatever you're doing. 90% of the time, that's all you need. Just do that stuff correctly, and you'll be okay. Anyway, so that's what I wanted to show you. Unless we got any questions or anything, I'm going to stop talking, and I'll go up and see if anybody needs help in the lab. Here comes a chat message. Before the end of class, could you give a hint how to complete Project 3? All right, let me take a look at Project 3. Cracking AES. Oh, yeah, this one should be easy. I think I remember some reasons why people get stuck here. The main reason people get stuck here is they don't count the bits correctly, in my experience. Let's take a look at Project 3. So here you're using CryptTool to try to crack AES with weak keys. CryptTool has the ability to feed in AES and feed in part of a key. So here's a key where you know everything except for the last 24 bits. This star is 1 byte, so this is 3 bytes. So you know most of the key and only 24 bits are left. So you only have to try 2 to the 24 calculations, which is 16 million, and any computer program can do 16 million pretty fast. So that's what this does. So here it will brute force attack them and find it. And it did find the plain text in some reasonable amount of time, which in this case was German. So I gave you a challenge where here, again, the key is all zeros except for the last 24 bits. So all you have to do is the same thing, but you have to go back here and replace all of this stuff with zeros except for the last 3 bytes. One thing I've seen a lot of students do is put 6 bytes of stars here because they think it takes 6 bytes to add up to 24 bits. And then, of course, it will never get there because it's far too many calculations to be done. And then down here is the same kind of story. The key is all F except the first 12 and the last 12 bits. That's another place where people often get in trouble because 12 bits is 3 of these characters. This is a nibble, which we did. This is 4 bits, this is 4 bits, and this is 4 bits. So the 12 bits are star at this end, and star at that end. And what a lot of students do is put 6 stars here and 6 stars there. And again, that makes it way too many calculations. That makes it 256 million, which is too many. So that's the main reason why people get in trouble that I've noticed is they don't count the bits correctly. So I hope that helps. Any other questions? All right, well, I'm going to stop this. I'll go upstairs and see if anybody wants help here. And I guess I'll see you next week. I thought we were doing easy CTF, but easy CTF seems to be gone. So we don't have a fun CTF to do, which is a drag. So farewell.